Hey everyone, in this video I'm going to talk about one of the most powerful problem-solving strategies that you can use on the ACT math section. This technique is one of my favorites to teach students, and I always teach it in the very beginning. The reason for that is that I've worked with hundreds of students at this point, and I always ask myself, if I could teach this student in the next hour only one thing, what would that one thing be that would allow them to get significantly more questions right? And it almost always comes down to knowing this particular problem-solving strategy. So what I'm going to do today is I'm going to work through 5 questions taken from real ACT math sections, and I'm going to solve them using this particular approach. The approach, I refer to it as giving yourself an example, and it'll make a lot more sense once we get into the questions. So let's just jump right in. All right, so as I mentioned, I refer to this technique as giving yourself an example, and basically we're going to want to use this technique in situations when the ACT is being very vague or general in the wording of its questions. And for each of these questions that we're going to work through, I'm going to solve them using this technique, and I'm also going to solve them algebraically or mathematically afterwards, just to demonstrate that there are multiple ways of approaching these questions. And ultimately, you're going to just want to choose whatever is most comfortable for you. So this question says that a number is increased by 25%, and the resulting number is then decreased by 20%. The final number is what percent of the original number? Okay, so in this question, are they giving us an actual number to work with here? They are not. All that they're saying is that a number is increased and then decreased. So since they're being very general, this is a situation where we could give ourselves an example. Now, part of the art of using this strategy, and this sort of comes through practice and experience, is choosing numbers that are easy to work with. So in particular, since they're giving us percentages here, we need to take percentages, I would choose a number like 100, because it's very easy to take a percent of 100. In fact, 25% of 100 is just 25, and etc. So let's go ahead and choose that as our original number. And the more you can sort of write this stuff down, the better, just to keep track. So the original number is going to be 100. And it says that we're going to increase that by 25%. Well, as I said before, 25% of 100 is just 25. So since we're increasing 100 by 25, our new number, let's call it the resulting number, since that's the way they worded it, the resulting number is going to be 125. Okay? Now it says that that number is then decreased by 20%. So we're going to want to find 20% of 125. And to do that, we can just do 0.20 times 125. And that equals 25. Okay? So now we're going to decrease 125 by this 20%, or by 25. And that will be our final number. So final number, and 125 minus 25 is obviously 100. So it says the final number is what percent of the original number. And since our final is 100 and our original was 100, it's clearly just 100%. So our correct answer here is C. Now, the really cool thing about this technique is that you can actually choose any number to work with. We chose 100 because that's easiest in terms of taking a percent, but just for the sake of showing that we can choose any number, let's go ahead and do this again, but just with a different number. Just sort of, I'm gonna just randomly pick a number here. Let's make it 20. So original number is 20. And we are increasing that original number by 25%. So let's find 25% of 20. Well, that equals 5. And if we're going to increase 20 by 5, our resulting number is going to be 25. And if then we're going to decrease that resulting number by 20%, let's find 20% of 25, so 0.20 times 25. That's just 5. So we're going to decrease 25 by 5, and that's going to give us 20. So the final number is 20. And just like before, 20 is obviously 100% of 20. So the final answer is C. And you can choose any number you want again, and you will get the same answer. Some numbers will be kind of cleaner to do than others. You might get like a decimal if you use a different type of number, but you'll still get as your final that it's 100% of the original. All right, so as I said, I'm also going to solve this now sort of using just algebra, just so you can sort of see that. And instead of actually giving ourselves an example, we're just going to use a variable here. So it says a number is increased by 25%. Let's just say that our original number is x. Okay. And if we're going to increase it by 25%, one way to express that algebraically is x plus 0.25x, right? And we can sort of combine like terms here. You can sort of imagine there being a 1 in front of that x. So 1x plus 0.25x, that's going to be 1.25x, okay? And now we are going to get our final number by decreasing that by 0.20 or by 20%. So we can write that as 1.25x minus 0.2 times 1.25x. Okay. And you could do this, on the calculator just to sort of see what you would get here. It just equals 0.25. So this, I'm going to write it up here as 1.25x minus 0.25x, and that is just 1x, which is what we started with here. So we get that it is 100%. All right, so that would be like an algebraic way of solving the question. And either way, whatever way you're more comfortable with is great. All right, so now let's go on to the next question here. And this one says that Jerome, Kevin, and Seth shared a sub sandwich. Jerome ate half of the sandwich, Kevin ate 1/3 of the sandwich, and Seth ate the rest. What is the ratio of Jerome's share to Kevin's share to Seth's share? And as before in the previous question, are they giving us an actual value here for the size of the original sandwich? They are not. All they're doing is telling us fractions of that sandwich that were eaten by each of these three people. So if we wanted to solve this giving yourself an example, you could just give yourself an actual number for the size of the original sandwich. And again, let's choose a number that's going to be easy to work with. Since Jerome ate half of it and Kevin ate 1/3 of it, let's choose a number that is easily divisible by 2 and easily divisible by 3. The first number that comes to my mind here is 6, so let's make this sandwich 6 inches, so 6-inch sub. And if Jerome ate half of it, that means Jerome will have eaten 3 inches. And then if Kevin ate 1/3 of it, that means that he will have eaten 2 inches. And then Seth ate the rest. So together, Jerome and Kevin ate 3 plus 2 is 5. So there's 1 inch left here. So Seth ate 1 inch. And they're asking us for the ratio of Jerome to Kevin to Seth. So that's just going to be 3 to 2 to 1. And that would be answer choice D right here. Okay. Now, again, you could choose a different number other than 6. You could have chosen 12, and you would have gotten ultimately the same answer. You might have had to simplify a little bit more, but you'd get the same result. All right, so let's also solve this just using regular math here. It says Jerome ate half the sandwich, Kevin ate a third, Seth ate the rest. If we want to compare the ratios of what they're eating, one way we could do that is by getting a least common denominator for each of these fractions in order to be able to compare how much they ate a little bit more easily. So the least common denominator between 1/2 and 1/3 is going to be 6. So to get this in terms of a sixth, we need to multiply both the numerator and the denominator by 3. So let's do that. 3 over 3 times 1/2, that gives us 3 over 6. And then to get this to be in terms of the sixth, we need to multiply the numerator and denominator by 2. So that would be like this. You get 2 over 6. And so now, Jerome ate 3/6 of the sandwich, Kevin ate 2/6. That leaves us with Seth, who would have had the remaining part, and that's going to be just 1/6 of the sandwich. And if we're going to compare the ratios, we can just do it's 3 to 6 to 2 to 6 to 1 to 6, and that just simplifies to the answer we got before, which is 3 to 2 to 1. Okay, so again, that's a little bit more abstract in a way than just giving yourself an example, but if you're comfortable with that, then that is totally fine. Let's go to the next question. So this question seems to be involving some geometry, obviously. And we're told that ABCD is a square, and points are chosen on each pair of adjacent sides to form 4 congruent right triangles. So we have these right triangles here. And it says each of these has one leg that is twice as long as the other leg. So we can see here they've represented that algebraically as x and 2x. And then it says what fraction of the area of this bigger square is shaded. Okay, so one way of solving this question, since they're trying to get the fraction of the area of the big square that's shaded, would be to find the area of the shaded square and then divide that by the area of the bigger square. And that should give us our final answer. I'm just going to go ahead and actually label the fact that these are right triangles, because as soon as you read a question on the ACT, it's a good idea just to label as much as you can so you don't have to keep all that information in your head. All right, so we have all these right triangles. We have that this side's 2x and that this side is x. As we said before, we want to get the area of the shaded square here. Well, to get the area of a square, we would want to know the length of a side. And then once we have the length of the side, we could just multiply it by itself, basically, because all squares have sides that are the same length, and that would give us the area. All right, so one thing about this question is that they're giving us just x and 2x, and it can be a little bit hard to think about that because it's a little bit abstract. So let's give ourselves an example for what those numbers could actually be. And I'm just going to choose an easy number, like let's say x equals 1. So we just write that down, x equals 1, and that would mean that 2x is equal to 2 times 1, which is just 2. All right? So essentially here we have a right triangle where this side's 1 and this side's 2. And as we said before, we want to get what that side is. So since it's a right triangle, we can use the Pythagorean theorem to calculate that side. Pythagorean theorem says that one side squared plus another side squared of a right triangle is going to give us the hypotenuse squared. And what we're looking for here is the hypotenuse. So let's plug in the numbers that we know. We have one side is 1. So 1 squared plus the other side, which is 2. plus 2 squared, and that's going to equal c squared. So 1 squared is 1, 2 squared is 4. Putting those together, we have 5 equals c squared. And so the square root of both sides here would give us that c is equal to the square root of 5. So let's go ahead and label that. We have the square root of 5 right there. And since it's a square, all sides are the same length. So this side would be square root of 5, that would be the square root of 5, and that would be the square root of 5. Now to get the area of the shaded region here, we're just going to multiply square root of 5 times square root of 5, because that's how you get the area of a square. Multiply both sides. So square root of 5 times square root of 5 is just equal to 5. So that is the area of this shaded region. Now, as we said before, we need to get the area of the bigger square. And so let's see how we could do that. Well, we were told originally that these are 4 congruent right triangles that make up this bigger square over here. So each of this, like this one right here, is going to also be 1 because it's congruent, which means it's the same, has the same lengths as the other triangles here. So that would be 1. This is going to be 2. This would be 1, and this would be 2, and this would be 1, and this would be 2, right? So now, since we want the area of the bigger square, we know that this side right here is 3. In fact, all the sides are 3. So the area of the bigger square is going to be 3 times 3, which is 9. And so the fraction that's shaded would just be that 5 that we found before over the bigger one, which is 9. So our correct answer here is just 5/9. All right, so let's also solve this algebraically now. And instead of just plugging in a number for x, we are going to just use x and leave it as it is, right? But we're just going to do it basically the exact same way as before. Again, we're going to want to get the length of this side here. And to do that, we'd again use the Pythagorean theorem. So it would be x squared plus, you have to be careful about how you write this, parentheses 2x squared is equal to c squared. And when we do the math on that, we'll get x squared plus 4x squared is equal to c squared. And then from there, it will be 5x squared is equal to c squared. And taking the square root of both sides, we'll get that c is equal to the square root of 5x squared. And you can sort of simplify this because we could pull out an x from this x squared part since it's a square root. So it would be x times radical 5 is equal to c. So I'm going to label that right here, x rad 5. And to get the area here, again, each of these is going to be x rad 5. We can just do x rad 5 times x rad 5, and that is going to be x squared times 5, which is the same thing as 5x squared, just rearranging the numbers there. Okay, so we have that the area of this is 5x squared. Let's again find the area of the bigger square here, and again we can just label each of these sides since these are all congruent triangles like that. And again, the whole thing will just be 2x plus x, which is 3x. So to get the area of the bigger square, we'll do 3x times 3x, which is 9x squared. And to get the fraction, we're going to do the 5x squared that we found earlier over 9x squared. And those x squareds are going to cancel out and leave us with 5/9. Okay? So we get the exact same answer. Now, the reason why, for example, giving ourselves an example can be useful here is because sometimes I've seen that students will get kind of lost in the algebra here. There's a couple potential mistakes you commonly make, or people commonly make here. One is they sometimes forget to put parentheses around the 2x, and they end up getting, instead of 4x squared, they'll get like 2x squared there, and so they'll get the wrong answer. Another thing is it takes a little bit of comfort with dealing with radicals in order to sort of simplify this 5x squared part and pull out the x. Again, if you're comfortable with algebra though, definitely feel free to do it that way. And by the way, there are other ways of solving this question other than the ones we just did. So if you got the same answer, feel free to just use whatever is working for you as well. Let's go to the next question now. So this question says that for all x in the domain of the function here, this function is equivalent to. All right. This is a great question to give yourself an example with. And a lot of people, it doesn't even occur to them that they could use it here. But again, the wording of the question gives us a lot of flexibility. It says for all x in the domain of this function. So basically, we can choose any number for x as long as it won't violate the domain of this function, or as long as it's in the domain of that function. So you might need to know a little bit about domains here to choose a number, but basically for our purposes, all we need to know is that as long as the denominator isn't equal to 0, then the number is fine and it will be in the domain. The only number here that will make the denominator equal to 0 would be x equals 0 or x equals 1. If you plug in either of those, you're going to get 0 on the denominator. So we want to avoid these two numbers here, just like crossing these out. But other than that, we can choose any number. So let's choose, for example, x equals 2. All right? And it says it's asking what is this equivalent to? Well, we're just going to plug in 2 anytime we see an x here. So x plus 1 over x cubed minus x is just going to be 2 plus 1 over 2 cubed minus 2. And if we're going to simplify that, that's going to be 3 over 8 minus 2, which is 6, which is 1/2. Okay. Now that we have our answer, now that we see what this thing is actually equal to, the next step is we go to each of these answers and we plug in x equals 2, because that was the number we originally chose. And whichever answer gives us this is going to be the correct answer, as long as there's not more than one that works. So let's go ahead and try this out. So for f, this is going to be 1 over 2 squared minus 1 over 2 cubed. And that's the same thing as 1 over 4 minus 1 over 8. And if you want, you can plug this into your calculator just to see what it equals. And you should get that is equal to 1 over 8. And that's not what we want. We want to have 1/2. So that's gone. Let's try g out, and I'm just going to write it down here for space. So this would be the same as 1 over 2 cubed minus 1 over 2. And that is the same thing as 1 over 8 minus 1 over 2. Again, feel free to use your calculator here. That is going to be equal to negative 3 over 8, which again does not work. Let's try h out. So h is going to be 1 over 2 squared minus 1. And that's the same thing as 1 over 4 minus 1, which is 1 over 3. We want to get 1 over 2, so that's gone. Let's try j out. That's going to be 1 over 2 squared minus 2, which is 1 over 4 minus 2, which is 1 over 2. So that works. Now, when you're using this technique, you want to check all the answers, because even if one works, it's possible that another answer will also work, in which case you can still eliminate everything you eliminated earlier, but you just have to choose another number to further eliminate between those two. So let's quickly check out k here. So if you plug in 2 there, you get 1 over 2 cubed, which is 1 over 8, which also does not work because we want 1 over 2. So j is the correct answer. Okay? So now let's solve this algebraically as well. So one way to solve this algebraically is this is what we're starting with. And in general, it's a good idea when you're trying to rewrite an expression, and that's kind of what we're trying to do because we're trying to find what this is equivalent to. A lot of times factoring is involved here. So I would ask myself, is there anything I could factor here? And what you'll notice is that on the bottom, we could actually factor out an x. So let's rewrite this as x plus 1. Let's take out an x here. That would be x times x squared minus 1. And then from that point, what you'll also notice, if you're familiar with this is the difference of two squares. And if you're not familiar with this, don't worry about it. Feel free to just give yourself an example and solve it that way. But you can rewrite the difference of two squares as the first number plus the second number. times the first number minus the second number, like that. So we get that. And then from there, you'll see that we could actually cancel out the x plus 1 on the top with the x plus 1 on the bottom. And so we're going to be left with a 1 on the top and just an x times an x minus 1 on the bottom. And looking at the answer choices here, we don't see anything that matches up with that immediately, but we could then actually just redistribute the x here, and that would be 1 over x squared minus x, which is j, which is the same answer that we got when we gave ourselves an example. Okay, so essentially the algebraic approach is wonderful and great, but as with one of the other questions we saw earlier, it does require some familiarity with some of these concepts, right? Like you would need to know how to factor the bottom here to get that first step, and then from there you'd have to be familiar with the difference of two squares to get to that next step. So if you're good with all that, great, do it that way. Otherwise, feel free to just plug in a number and see what you get. All right, so we have one more question here. And it says, for all real numbers b and c, such that the product of c and 3 is b, which of the following expressions represents the sum of c and 3 in terms of b? Okay, so that's a very wordy question. It's a number 59 on one of these real ACT math tests. So a lot of times when people see this, they kind of just get overwhelmed by all the wordiness of it. And also the fact that it's pretty abstract, because instead of giving us actual numbers, they're giving us variables to work with here. And that's a very common technique that the ACT uses just to intimidate and freak people out, basically. And as before, what we can do here is we can just give ourselves examples for these numbers. So let's see here. It says for all real numbers b and c, such that the product of c and 3 is b. Now we need to be a little bit careful with how we choose these numbers, because they are giving us an actual equation here, or a restriction on the relationship among these numbers. So let's say that c is going to be 4, for example, right? Well, we know that the product of c and 3 is b. So we can't just choose any number for b now. We have to actually just choose 12, because it says the product of c and 3 is b, and we chose 4 for c. So that's a situation we just have to kind of go with that number. Now it says, which of the following expressions represents the sum of c and 3? And we have said that c is just 4. So what represents the sum of c and 3? Well, what is the sum of 4 and 3? That's just 7. In terms of b, so in terms of 12. Okay. Well, as we showed before, once you get your answer, and the answer here is just 7, we're trying to get the sum of 4 and 3, so it's just 7. Once you get your answer using this technique, you then go to the answer choices, and you see which one gives you that answer out. So let's start off with answer choice A here. So A says that b plus 3 will give us what we're looking for. Well, we chose 12 for b. So this is the same thing as 12 plus 3, which is 15. The answer we want is 7, so that's gone. What about b? So that would be 3 times b, which is 3 times 12 plus 3. And just off the bat, we can see that would be too big. In fact, 3 times 12 is 36, plus 3 is 39, so that is not 7. That's gone. For c, let's see what this equals. B, again, is going to be 12. So this is the same thing as 3 times 15, which is 45. That's not what we want. Let's try d out here. So that would be 12 plus 3 over 3, which is 15 over 3. And that is 5, which again is not what we want. So that's gone. And then for e here, that would be 12 divided by 3 plus 3, which is 4 plus 3, which is 7, which is what we want. So e is our correct answer. So by giving ourselves an example here, we took a really kind of abstract, wordy complicated looking question and made it much easier to deal with. And really that's a lot of what the ACT math is all about. A lot of times they're trying to intimidate us and make things look really hard and complicated, when in fact the underlying math behind most math questions on the ACT is relatively basic. Like here, all we're really doing is addition, subtraction, multiplication, and division. I mean, it's like basic stuff, and it becomes much easier when we make these numbers concrete. All right, so now let's go ahead and solve this algebraically. And one way we could start with that is just by writing down what we know. So we know that the product of C and 3 is B. Well, product, that just means to multiply. So the product of C and 3, so C times 3, and then is B, so equals B. And it says what expression represents the sum of C and 3 in terms of B. So really what we're looking for at the end of the day is the sum of C and 3. But instead of using C, they want us to use B somehow in this final thing. So all we really have to start out with here is this piece of information right now. And since we want to go eventually down here and just use B, the idea is that we need to re-express C in terms of B. In other words, we need to find out like how C and B are exactly related and then just plug that in down here. Well, to do that, we can start with this equation and just get C by itself. Right now, we're multiplying it by 3. And to get rid of that 3, we need to divide it by 3. So if we divide both sides of this thing by 3, what that leaves us with is C is equal to B divided by 3. And as we said before, we want this final thing here, but instead of using a C, we want to use B. So now we have an equation that relates the two directly. So instead of writing C, let's replace that with B divided by 3. So this just equals B divided by 3 plus 3. Okay, and we're basically done. That's what we wanted to find. And again, just as we saw earlier, we are going to get the same answer as when we gave ourselves an example. Now, if this sort of algebraic approach is confusing in any way, don't worry about it. Like the algebra here is kind of abstract and it takes some getting used to. But you don't need to know or really understand it deeply if you're going to use the strategy of giving yourself an example. And that's the beauty of that. All right, so hopefully those questions gave you a good sense of just how powerful this technique is. As you can see, we solved a bunch of different types of questions using the same technique. We solved a question dealing with percentages. We solved a question with ratios. We solved a question on geometry and Pythagorean theorem. And then we also solved a couple questions involving algebraic re-expression using giving yourself an example. And that's what I was saying earlier, that if you could just learn only one skill, like what is the best bang for your buck? And this strategy is one of the top 2 that I would recommend for just that. Now, the next step in really getting good with this is becoming comfortable with identifying when exactly you can use it, like what questions that it works with. So one of the best ways I recommend for practicing that is just find a real ACT math section and don't time yourself on it. Just kind of browse through it and try to identify questions that you could use this technique on. Again, one of the big giveaways is if it's like very vaguely worded, or if they give you a variable in the question that you can also find in the answer choices, for example. And once you get really good at sort of recognizing when you can use this technique, then when it comes time to take a real ACT or just like even a timed practice test, in those situations where you have all that pressure, you're just automatically going to know to use it, and it will be easy for you to do. So good luck with that, and I'll be making other videos on other strategies that you can use on the math section.